how they are related to the wear and friction behavior of PTFE and its composites. A quick review on what PTFE is. So PTFE is a stands for polytetrafluoroethylene, and the chemical structure of PTFE is seen in this image. So you have a carbon and carbon bonded to each other, and each carbon atom is bonded to two fluorine atoms covalently. And the structure inside these two parentheses keeps repeating to form a very long chain. The applications of PTFE are sliding and dry lubrication applications, and the properties which allow these applications are its high melting temperature, low friction coefficient, and chemical inertness. The main problem with the usage of PTFE for extended periods of time, however, is that it has a very high wear rate, roughly in the order of magnitude 10 to the negative 3 mm³ per annum, and a lot of research has been done over the years to improve its wear rate by changing different parameters, as we have seen in the earlier two presentations. In this presentation, we'll be looking at the counterface roughness, wear debris mobility and roughness angle, humidity, vacuum environment, mechanochemistry, cryogenics, and irradiation. So how changing these factors results in improved wear rates and friction values. So first of all, uh, in this study, we'll be looking at the counterface roughness. So as you can see, uh, in this study, the research group kept the counterface material the same. So they used grade 304 stainless steel for all measurements, but they changed the surface finish from electropolished, lapped, wet sanded, and dry sanded. And the highest roughness was seen for the dry sanded, and the lowest roughness was seen for the electropolished. So let's look at the friction results. As you can see in the friction results, the values of the friction coefficient are concentrated in the range from 0.12 to 0.19 approximately, which suggests that friction coefficients are not very sensitive to changes in the counter surface finishes. On the other hand, if you look at the wear rates, the lapped surface finish performs the best because it provides the lowest wear rates for all of the samples. So if you look at the 44 nm, 80 nm, and 500 nm, the lowest wear rate is seen for lapped finish. Another interesting thing to note on this graph is that unfilled PTFE is not very responsive to the changes in surface finish because it does not have any change in the wear rates. It's still very close to 10 to the negative 3 mm³ per annum. So the research group suggests a very interesting idea here. So they looked at the surface of the counterface, and they suggested that the reason why lapped surface finish was providing the lowest wear rates was because of its negatively skewed geometry, which provided greater contact surface area, and thus improved the mechanical engagement, allowing a stable and uniform transfer film to form. Also, the negatively skewed shape of the surface uh, allowed reduced abrasion, meaning that during sliding, the uh, the amount of scraping of the surface was decreased, and this allowed better and stable transfer films to form. So if you look at these this is another evidence of what was going on at the surfaces. So if you look at the wear rates are lowest for this sample with sample C. So look at the changes, or look at the ranges of thickness seen for the sample. So for sample C, you can see that the thickness is, for sample C, you can see that the transfer films are very thin and are pretty uniform as compared to other samples which have higher wear rates. So in this study, the research group suggests that there is a strong relationship between the uniformity and thinness of the transfer film. And this particular concept, or this particular statement that I just said, we'll be seeing this repeatedly in further studies as well. So in this one, this is the study which deals with alignment of the roughness with respect to sliding direction. So in the earlier study, we had roughness, but it was not aligned in any particular direction. But in this one, we're aligning it with respect to the sliding direction. So as you can see from these images, uh, the 0 degree angle means that the roughness is parallelly aligned to the sliding direction, and the 90 degree means that the roughness is aligned 90 degrees or perpendicular to the sliding direction. And you have also so also they also changed the type of finish from lapped to polished. So these are the results for wear rates. The best wear rates are seen for 90 degrees lapped and polished, and the wear rates are in the ultra low wear region. And on the other hand, the highest wear rate is seen for the 0 degree um, roughness alignment with respect to sliding direction. These two graphs are basically telling the same story as this one, because if you take the derivatives of these graphs, you should get this. You should get this graph. That's because that's the definition of wear rates. Now, if you look at this graph, you can see that the 0 degree angle has the steepest curve, which corresponds to highest wear rates. And if you look at the 90 degrees lapped and polished finishes, you have the shallowest curves, which correspond to low wear rates. And because these are the lowest wear rates, and if you focus on particular um, these three particular um, I should say parameters, then we have, and when we zoom into them, we can see that the lowest wear rate is for the 90 degree angle, because that has the shallowest curve. This one looks at the transfer film formation on the counterface. So increasing the angle from 0 to 90 degrees results in an improved coverage of the counterface. So coverage in this case means that the amount of counterface that is covered with the transfer film. So as you can see, for 0 degree angle, you have very low coverage of the coverage of the transfer film. Coverage of the counterface, which results in the highest wear rate. And with the increasing angle, the coverage is increasing. And if you look at the lapped and polished finishes, even these two finishes have a very high coverage, and because of that, they also have lower wear rates. Now, this research group suggests two models as to what is going on at the surface, at the counterface. And both of these models are connected to the mobility of wear debris. So first model suggests the amount of obstacles that are faced by the wear debris, and the other one looks at the friction experienced by the wear debris. So basically, both of these models are trying to show that depending on the mobility of the wear debris, where where can be increased or decreased. So if the wear debris is extremely mobile, then the wear rates are likely to be high, and if the wear debris is not so mobile, then the wear rates will be very low. They looked at they used their models and tried to compare the models with the experimental data, and you can see from this graph that the experimental data and the model suggested by the research group are very close to each other. However, the research group admits that this model is not the best or is not the most accurate, because it does not take into account the tribochemical reactions that occur at the counterface. But one interesting thing here is that if you looked at the results, or if you looked at the wear rates between 0 degree and 90 degree, the 0 degree sample had the highest wear rate and the 90 degree sample had the lowest wear rate. So the roughness angle is basically is somehow involved in the entrapment and accumulation of wear debris. So when you have low roughness angle, so when the motion when the sliding motion is parallel to the roughness angle, the wear debris is not the wear debris is more mobile and cannot be trapped to the same extent as it can be trapped at a higher at 90-degree groove angle. And also, the decreased mobility of wet debris allows increased tribochemical reactions to occur, which again results in decreased wear rates. This one, in this one, the research group looks at the effect of humidity and environment on the wear and friction behavior of PTFE and PTFE alumina. So as you can see, they changed the relative humidity from 0.5% to 87%, and they changed the environment from nitrogen to nitrogen and oxygen. So before we begin, let me just explain quickly what relative humidity is. So relative humidity is basically a ratio of the amount of water vapor present in the air with respect to the amount of water vapor required for saturation at a constant temperature. And basically the environments, a nitrogen environment and nitrogen oxygen environment. So the nitrogen plus oxygen environment and the ratio, this is basically what we see or what we experience in our normal daily lives. This ratio comes very close to what is normally in our atmosphere. So beginning with the friction and wear results, if you look at this table here, this mu basically is a symbol for friction, and you can see that the friction values don't change much. The lowest friction is 0.1 and the highest friction is about 0.2. So the friction values are fluctuating, but they are still not changing drastically with the changes in the environmental conditions or humidity. On the other hand, if you look at the wear results, with the increase in humidity from 0.1 to a very high humidity percentage, you can see that the PTFE alumina samples are performing much better in both environments. So in nitrogen and oxygen environments, the wear rates keep going down with the increase in relative humidity. But if you look at the unfilled PTFE, for both environments, changing the humidity does not affect the wear rates. Another interesting thing to look at is that PTFE alumina in liquid water and in vacuum performs very badly, as it gives a very high wear rates, about 10 to the negative 4. So basically what this is trying to show is that too little or too much water is not good for the experiment, for the wear rate experiments. Now, these are the optical images of counterface of PTFE alumina at two different humidity conditions. So at 69% and 0.6%. So if you look at the profilometric scan of the counterface, you can see that the transfer film is thin and uniform for 69% humidity, and on the other hand, if you look at the 0.6% humidity, you have a very non-uniform transfer film with regions of very thick transfer films. And similar to that, you can look at the wear rates. This one has a 10 times higher wear rate than at a higher humidity. Now, if you remember, in an earlier research which dealt with the counterface roughness, the research group stated that there is a strong relationship between the transfer film thickness and uniformity and the wear rates, and that is basically seen in this research. So so if you look at the transfer films and the uniformity and the thinness of the transfer films, this sample performs better than this one, which is very clearly seen from these images. So this research group suggests a few reasons as to why wear reduction occurs. So first of all, the gaseous water vapor is required for facilitation of certain tribochemical reactions, which basically is seen from the wear rate graph. So increasing the humidity resulted in a monotonic decrease in the wear rates. On the other hand, liquid water, if you completely submerge the sliding environment in liquid water, then the wear rates are high. which means that liquid water somehow is responsible for inhibition of stable transfer film formation. And when we looked at the friction values changed, but they didn't change drastically and were in the region between zero point 0.1 and zero point 0.2. And the research group says that there's no clear trend between environmental and humid conditions for friction coefficients. And finally, the role of oxygen is still not completely understood. As you can see from this graph, for PTFE and alumina, uh, in both nitrogen and oxygen conditions, the wear rates kept decreasing with increasing humidity. So clear that what oxygen is doing in this particular case, how it is involved, is not known yet. This study deals with the vacuum environment, and as you can probably guess, this study and the earlier study are related in the sense that changing the chamber pressure is basically a process in which the amount of air present in the chamber will be changed. And basically, if you change the amount of air, then you'll be changing the amount of nitrogen, oxygen, and gaseous water vapor present in the air. So there's a relationship between those two studies, but it's not a direct relationship. They are related, however. So if you look at the friction results, clearly there's not a drastic change, and this we've been seeing for since almost all the research articles that we have reviewed so far. The friction is not changing drastically, but notice you can see that there's a that the PTFE alumina performs worse than just PTFE at low sliding and at low chamber pressures and high chamber pressures. In this particular slide, we'll be looking at the counterface and the transfer films on the counterface. So if you look at the wear debris at 760 torr, you can see that the wear debris is very large and is plate-like, as compared to at 5 torr and 110 to the negative 2 torr, where the wear debris is not as big and is patchy and plate-like. And these results are very important, as you'll see in later slides. Similar to the unfilled PTFE alumina shows similar results, where you have, except that the amount of wear debris seen is much lesser, and the transfer films are much more thin. So you can see that for 760 torr, you have a thin region of wear debris in the transfer film, and at 5 torr, you have an even thinner transfer film and even less of wear debris. Now these results, because these are qualitative results, a profilometric scan is done to actually quantify the thickness, the average thickness of the transfer films, and you can see those here. So in the case of unfilled PTFE, you can see how the variations in the transfer film thickness occur, and you can see the same thing in PTFE alumina. So at 5 torr, you have the most thin and uniform transfer film, and this is very significant because you will see why it is significant in this particular result, where you have wear reduction occurring, or the lowest wear being observed for the 5 torr. So the 5 torr sample has the most uniform and the thinnest transfer film. So again, as was stated in the earlier research, that there is a high dependence between wear rates and the transfer film thickness and uniformity. That same pattern is seen in this study as well. So this research group suggests that the wear rates are as seen because of the transfer film formation. So clearly, the better, thinner, and uniform transfer films are necessary for low wear rates. Again, at 5 torr, or in the range between 5 torr and 110 to the negative 2 torr, the wear rates are seen to be lowest because of the amount of partial pressure of oxygen and the environmental concentration of water vapor. So these two are, or the optimum amount of the environmental concentration of water vapor and partial pressure of oxygen is expected to be in the range in 5 torr and 110 to the negative 2 torr pressure ranges. However, the exact mechanism or the exact chemical reactions that are involved are not yet known. In this particular research paper, we'll be looking at the mechanochemistry. So this image is basically an image which represents something called a stripe test. Now, in a stripe test, what happens is that the PTFE composite is run to different is run to different lengths or covers different regions of the counterface for different cycles. So this particular region um, will be the first cycle, and then different regions will show you different cycles or the transfer films formed after different cycles. And the reason why this stripe test is so important or so relevant to the study is because it shows you the difference between the initial phases and the final phases. Because now in this paper we are going to try to study the chemical reactions, and we are trying to study at what point in the reaction or in the sliding process do the chemical reactions start occurring, and that's why we need to look at different stages of the cycles. So first thing first, before we start looking at the chemistry, we can see this trend in the wear. So during the initial stages of the cycle, the wear rate is high, but with the increased number of cycles or more sliding distance, the wear rates fall. And this is basically because of transfer films forming with increased sliding distance, and these transfer films are stable. The coefficient of friction, on the other hand, does not have a drastic change with sliding cycles, so it's roughly in the range between 0.16 and 0.22. So looking at the infrared spectroscopy results, um, there are two main things going on here. So during the initial cycle, the first cycle, which basically covers the entire counterface, so it goes from the beginning or it goes from the starting point to the ending point, and that is the entire first cycle. So if you look at this particular graph representing the first cycle, it suggests, so there are three peaks here: 1203, 1149, and 1253. So these two peaks are seen for carbon-carbon and carbon-fluorine bonds, but this peak at 1253 is a new peak, and this suggests that the transfer films um, that are formed, or the layers of PTFE that are transferred onto the counterface are aligned. And after sliding to achieve higher sliding distances and increased number of cycles, the even further new peaks are seen, indicating that a chelation process has occurred. And I will talk about the chelation process in the further slides. So this group suggests an explanation for wear reduction in terms of mechanically driven chemical reactions. So what they are suggesting, so why is this paper called, or why have I used the term mechanochemistry here, or why has the term mechanochemistry been coined for these particular reactions? So mechanochemistry is basically coined because the reactions that are occurring are mechanically driven. So there are stresses and forces involved that basically induce chemical reactions, and the mechanics is described here. So there's uh, there's a breakage of forces occurring. So there's a competition between van der Waals forces and the force required to break a PTFE fibril. So as you can see here, when the PTFE fibril breaks because of the stresses acting on the fiber, what happens is that new surfaces are exposed, and um, and this results in increased possibility of chemical reactions to occur. And what happens is that when when a PTFE backbone breaks, then the PTFE chain breaks. What happens is that the end groups are possible, or it is possible for the end groups to form new chemical bonds, as you will see on the next slide right here. So when the PTFE fiber breaks, you have the end groups which can basically form um, new chemical reactions. So basically, in the first case, the fiber breaks, and then you have even further breaking going down, and in the presence of oxygen and water, you have new chemical species being developed. So here you have a carbon bonded with uh, double bonded with an oxygen and a hydroxyl group. So you have a carbon OH bond, and then finally these break down to form metallic chelates. So these groups, basically COOH groups, are like carboxylic acid end groups, and they can react to, so this hydrogen, so this OH group can basically uh, get further split to form or to react with the metallic uh, uh, elements present either on the counterface or the alumina, which is basically the filler metal. And this is the chelation process. So in A you have mechanical sliding, which is basically the mechanics that is involved in the breaking of the bond. Then you have environmental oxygen and water reactions. In this paper, we'll be looking at the cryogenics, which is basically changing the temperature. But this is a very interesting study because in this one, the research group created a cyclical loop wherein initially they were at room temperature, and they increased the temperature to 433 Kelvin, and then from 433 they came back down to 148 Kelvin. And they also changed the relative humidity between 2% and 6%. Now let's look at the friction results. So what is going on here? First of all, in region A, with the increase in temperature, the friction values kept decreasing. Why was that seen? And that was seen because so first, before I explain that, let me make it clear that there is no composite involved here. It's pure unfilled PTFE for both. So when we're measuring the wear and friction, we will be looking at only unfilled PTFE. So in the case of A, in this region, there's something called viscoelastic properties of PTFE, and we have seen this in an earlier study involving sliding temperature in the second topic in the presentation, which took care of the second topic. So the viscoelastic properties and the softening of PTFE makes the friction coefficients fall to lower values when the temperature is increased. And when you go and when the temperature is decreased before the frost points, there's a sharp increase in the friction coefficients, and then there is a very small increase after the frost points have reached in this region B, uh, and then once the highest friction coefficient is reached, there's a sharp decrease in the value of friction coefficients. So so let's understand what is going on in this graph. So frost points are basically points at which the water vapor present in the atmosphere um, precipitates to form ice. So the temperature is very small, such that now the water vapor can't remain as water vapor, and it becomes ice and gets deposited on the counterface. So in this region, what is going on is that you have ice forming, and that is basically the reason why the friction values are fluctuating. In region C, on the other hand, what's going on in both regions, in region C and D, what's going on is that friction values are going down because now the ice is melting to form water. And the reason why that is happening is because your friction causes heating, and that heating results in the melting of ice. So This cyclical process suggests the transformations of the water vapor from a gaseous state to a solid state and then to a liquid state, affecting the friction values. But again, the friction values are not changing by a huge margin. Looking at the wear rates, again, this is a cyclical process. So if you start from this from the higher from the normal environmental temperature, which is about 299 298 Kelvin, increasing the temperature decreases the wear rates. Again, reasoning is the same as the uh, as why friction values decrease, because of the softening of the polymer. And then based on hysteresis, again, similar trend is seen until the uh, 298 Kelvin temperature is reached, which is basically the room temperature, wherein decreasing the temperature increases the wear rates. But there is the research group says that there's no way to explain, or they have not found a reason as to why between 298 Kelvin and two somewhere between 280 Kelvin, why was the wear rate increased so much. So they were not able to understand why there was this sudden rise in the wear rates. However, as the after reaching the frost points, the wear rate started to decrease again uh, in the mild wear rate range. And again, the reason for these observed wear rates is similar to the reason why we observe the friction coefficients, wherein there's a phase change of gaseous water vapor to ice to um, liquid. And the reason, or the main reason why these changes are occurring in terms of wear rates, is because of the changes in the transfer film. So initially, the sliding interface is PTFE on PTFE, but when ice starts depositing on the counterface, it's PTFE fused or combined with PTFE and ice, or ice deposit on the transfer film, and finally there's PTFE, water, and ice. So all of these changes are basically affecting the wear rates. So again, suggested explanation for the trends that are seen in wear and friction is that we have viscoelastic properties and softening of PTFE at higher temperatures that are considered. So viscoelastic properties are basically properties which deal with the elasticity and viscosity of the polymer. Then change in the sliding environment results from the change in the temperature, wherein the gaseous water vapor uh, sublimes to form ice, and then frictional heating results in the melting of this ice to form liquid. There's hysteresis involved, in which hysteresis basically means that the past state of the system is somehow influencing what the system is going to do, or how the system is going to react now. Um, and that's what is seen in this graph. The past state of the system, wherein it showed decreased wear rates for increasing temperature, this hysteresis was seen right here. So decreasing temperature resulted in increased wear rates. And finally, this was already predicted by the research group, that the friction values should increase um, at lower temperatures, and that's because of the increased mechanical properties at low temperatures. This is the final topic that we'll be looking at, and this was a very interesting study in which the surfaces were irradiated with a 225 kilo electron volts energy. Um, what they changed here again, in this study we have unfilled PTFE, so no composites, no PTFE composites and no fillers, just PTFE by itself. And the irradiation surface coverage was what they changed. So they had three different, so they had basically four different. One was unirradiated, 0% irradiation, so there was no radiation exposure. And there was 50% irradiation with interconnection. There was 50% irradiation with dispersed, and 100% irradiation. So I will explain these two. These two images will explain what the difference is. So if you look at the 50% irradiated dispersed, what it means is that um, uh, the irradiated surfaces are not interconnected, meaning that these two regions are basically irradiated surfaces, and any two irradiated surface regions are not connected to each other. And on the other hand, if you look at this one, the irradiated surfaces are interconnected, meaning that the white regions are basically the ones that were not exposed to radiation, and the black regions are ones that were exposed to radiation. Looking at the results for friction and wear, again, friction coefficient values have been changed, but they're again not changing by a lot. They're in the range between 0.05 and 0.2. However, it is interesting to see that the lowest friction coefficient value after achieving steady state was seen for the 50% dispersed irradiated. So 50% dispersed irradiated, meaning surface which had uh, 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 this kind of irradiation pattern. And similarly, um, if you look at the wear rates, the worst wear rate was seen for the 0% irradiation, and the best wear rate was seen for the 100% irradiation. But the 100% irradiation also accompanied the highest friction values. The best, if you look at the, if you only consider the sliding distance between 0 to 4,000 meters, then the best possible I would say best possible surface exposure to irradiation would be a sample with 50% dispersed irradiation, because in this particular region, the wear rate for the 50% dispersed irradiated was the lowest, and also the friction coefficient was the lowest. The research group suggests some explanation as to what is going on. So why the wear and friction values are affected. So first of all, the optical image of wear track of unirradiated, so 0% irradiation, suggests that there's a wear debris deposition along the wear tracks, whereas if you look at the 50% dispersed irradiated PTFE, the wear debris or the wear track is much smoother, with no evidence of any uh, debris. On the other hand, um, the other reasons as to why friction and wear properties were different is, first of all, because of lower friction and wear values for 50% irradiated sample, facilitation of non-abrasive adherence of self-lubricating transfer film. So what this basically means is that for 50% irradiated dispersed samples, the transfer film that is formed is not abrasive, meaning that it is not damaging the transfer film. It is adhered to the counterface, uh, which would mean that it's not going to easily be scraped off. If you look at the on top of that, um, the other trend that was seen in all of these graphs right here is that eventually, in spite of radiation, in spite of 50% radiation or 100% radiation, um, the wear rate skyrocketed after a certain sliding distance, and the reason for that is the consumption of irradiated regions through sliding. So basically, eventually, after enough sliding occurred, the irradiated surfaces were basically um, there was no contact between the PTFE composite, which was sliding against the surface, sliding against the irradiated surface, resulting in sudden increase in the wear rates. So, final conclusion of this particular um, presentation, we will look at both. We will just try to generalize or try to look at the summary of friction and wear reducing mechanisms that was seen in this presentation. So, if you recollect, almost all of the research groups uh, showed that the friction values did not change drastically when the different parameters were changed. On the other hand, though, for unfilled PTFE, steady state friction was lowest for the most surface irradiated sample. More interesting, more interesting trends can be seen for wear reducing mechanism though. So somehow, in all cases, the way different parameters affected wear rates, and the most important thing is that all changes in the PTFE or all modifications to PTFE, either by addition of fillers, by improving the radiation exposure to the surface, by changing the counterface roughness, always produced wear rates that were better as compared to unfilled PTFE. Um, and another thing that we looked at was the difference between randomized surface roughness and the aligned surface roughness. And uh, when we looked at the randomized surface roughness, lapped surface finish gave us the best wear rates. And when we looked at the aligned surface roughness, we got 90 degrees as the best surface, the best wear rates. Um, Finally, when we looked at the humidity and vacuum environments, we were able to understand that it is important to have gaseous water vapor present in the atmosphere for for good wear rates to be seen. And also, there's some influence of oxygen in the sense that partial pressure of oxygen is involved in the wear determining process, but exactly the role of oxygen is not yet understood completely. And based on all of this research, we still do not know how these different parameters are basically influencing each other. So we don't know the connection between these parameters that play into the improvement of the wear rates. And clearly, a lot more research is required. So before I um, before I conclude or before I stop, I would like to acknowledge the Miami University library resources and Google Scholar because I use those resources to find different articles. And I would also like to and I would also like to acknowledge the Kaltura recording tool because that is what I use to uh, make my videos. And thank you for listening. And I hope that these three uh, these three topics um, were helped you to understand different research that has been done over the years in the area of tribology and PTFE. Thank you.